the previous class, we discussed GATE 2024 1 mark question. Some few questions are solved, and in this class, we solve the rest question from 2024 GATE. So, the first question is a piston cylinder arrangement. Piston cylinder arrangement shown in figure as a stop located 2 meter above the base. This is the base. Here, the stop is located 2 meter above the base, and the cylinder initially contain 140 kilopascal pressure and 350 degree centigrade temperature. The piston is resting on equilibrium at the position which is 1 meter above the stop. This is the initially where piston is rested, and the system is now cooled to ambient temperature 25 degree centigrade. Consider air to be an ideal gas. This is the process constant. Consider air to be ideal gas with value of gas constant R equal to 0.287 kilojoule kg Kelvin, and the absolute value of specific work done during the process kilojoule per kg equal to how much? Kilojoule per kg, that means we have to treat mass is equal to 1 kg. So the given data will be, this is the position 1, so this is the position 2, and this is the position 3. As position 2 to 3, the volume does not change, and this is the closed system, so work done will be 2 to 3 P V2 minus V3. As V2 and V3, the position will not changes, V2 and V3 constant, that means work done will be 2 to 3 equal to 0. So we have to calculate it from 1 to 2 what is the work done. Work done 1 to 2 process, that means work done 1 to 2 will be P V1 minus V2, where 1 to 2 pressure is constant. So given pressure is 140 kilopascal and V1 V2 have to calculate it from ideal gas equation. PV is equal to MRT. As pressure is constant, volume directly proportional to temperature, so you can write it PV is equal to MR T1 minus T2. So directly we know volume, so temperature we have to know, where temperature T1 given 350 centigrade, converting it to 350 plus 273, that means equal to 623 Kelvin, which is T1, where the T1 value is 623, and T2 we have to know, and mass is 1 kg, and R given value 0.287 kilojoule per kg Kelvin, but T2 we have to calculate it. This is equation 1. As you know, V1 by V2 is equal to T1 by T2. So V1 is equal to area into this much length, that means 3 meter, and V2 is equal to this area into this length. Area into this length is 2 meter is equal to T1 given 623 Kelvin, and T2 we have to found. So T2 is equal to area into area 623 into 2 by 3, F2 equal to 415.3 Kelvin. By putting the value T2 in equation 1, we get W1 to 2 process is equal to 1 into 0.287 into 623 minus 415.3 we get 59.6 kilojoule per kg. So option A will be correct answer. Then the next question is, a heat pump is driven by the work output. A heat engine is shown in figure. The heat engine extracts 150 kilojoule of heat from source at 1000 Kelvin. The heat pump absorbs heat from ambient 280 Kelvin and deliver heat to the room, which is maintained at 300 Kelvin. Consider combined system to be ideal and total amount of heat delivered to the room together by heat engine and heat pump in kilojoule. What will be the answer? So this is the heat engine diagram and this is the heat pump diagram, and the process constant is have to assume to be ideal. That means follow the maximum efficiency by Carnot. So efficiency of, we know, heat engine is equal to 1 minus T lower by T higher. T lower means sink temperature and T higher means source temperature. That means 1 minus T lower temperature is 300 Kelvin, and where the higher temperature is 1000 Kelvin. That means 0 0 cancel. 1 minus 3 minus 10, that means 7 by 10 the efficiency, and which is equal to W net for maximum efficiency, W net by Q in heat engine. This is Q in, and where the Q in given 150 kilojoule. So W net, that means equal to 7 by 10 into 150. So 0 0 cancel. 15 into 7, that means equal to 105 kilojoule. So this work is given to heat pump directly, and this is also Q1 and this is also Q2 let. So from heat pump, by applying first law, this is heat pump, Q1 plus W net is equal to Q2, where W net is equal to 105 and Q1 is not known and Q2 is not known. So the heat pump COP, we know, this is TL divided by TL minus this is also T1. So this is also equal to refrigeration effect. That means this is Q2, and work input, this is W net, and TL given 300 divided by 300 minus T1 280 is equal to Q2 divided by Q W net we get from equation 105 by solving 300 minus 280 is equal to 20, and 300 divided by 20 is equal to 15. 15 is equal to Q2 divided by 105. So Q2 is equal to 15 into 105, which is equal to 1575 kilojoule. So Q2 is 1575 kilojoule, and by applying first law, in heat engine, Q in is equal to W net plus, this is also taken as Q3. So Q in is equal to 150 and W net is 105 plus Q3. So Q3 is equal to 150 minus 105, is equal to Q3 is equal to 150 minus 105 is equal to 45 kilojoule. So the question given, you have to find total amount of heat delivered to the room together by heat engine and heat pump. This means this will be how much and this will be how much. So Q3 and Q2 combine with that much heat provided to the room. So this heat amount is equal to Q3 plus Q2. Q3 as we get 45 and Q2 is 1575. By combining it, we get 1620 kilojoule, which is option C will be correct answer. So then next question, consider an air standard Brayton cycle with ideal compressor and turbine and refrigerator as shown in the figure. Air enters into the compressor at 100 kilopascal and 300 Kelvin and exit to the compressor 600 Kelvin and 550 Kelvin. The exist the combustion chamber is 1250 Kelvin and exits the adiabatic turbine at 1000 kilopascal and 800 Kelvin. The exhaust air from the turbine is used to preheat the air in regenerator. The exhaust air exits regenerator state 6 at 600 Kelvin. There is no pressure drop across the regenerator and combustion chamber. Also, there is no heat loss from the regenerator to the surrounding. The gamma value is 1.4, and we have to find thermal efficiency of the cycle in percentage. So let us draw the TS diagram. This is constant pressure process. This is also constant pressure process. This is isoentropic compression, and this is expansion. This is process 1 and 2, 4, 5 and 6. This is 3. Given data, T1 is 300 Kelvin as air enter to the compressor. This is one T1 and exit to the compressor 600 Kelvin. This pressure is constant is 600 kilopascal, and this is also 100 kilopascal as constant pressure. So the T2, the exit pressure of compressor, is 600 kilopascal and 550 Kelvin. The temperature is 550 Kelvin, and exit the exit of combustion chamber, that means exit means 0.4. T4 is 1250 Kelvin, and the exit of adiabatic turbine, this is the turbine where work will be produced, and work is given by compressor WC, and exit of the adiabatic turbine is 100 kilopascal and 800 Kelvin. So T5 is 800 Kelvin. And given the exit of regenerator state 6, this is also 600 Kelvin. So we know W net is equal to W turbine minus W compressor. So W turbine is per kg, we have to calculate specific work done is equal to Cp T4 minus T5 minus compressor is T2 minus T1 is constant pressure T2 minus T1, and Q reject, this is also Q reject is equal to Cp T6 minus T1, and Q supplied is Cp, to write in terms of W net, Q supplied is equal to W net plus Q reject. So we know efficiency, thermal efficiency is equal to W net divided by Q supplied, and W net is equal to Cp T4 minus T5 minus Cp means constant specific heat at constant pressure 2 minus T1 divided by Q supplied is W net plus QR. W net is Cp T4 minus T5 minus Cp T2 minus T1 plus Cp T6 minus T1. So Cp cancel from both numerator and denominator, and by putting the value T4, T5, T2, T1 is get efficiency of thermal efficiency is equal to, where T4 value is 1250 minus T5 value is 800 and T2 value is 550 and T1 is 300, and T4 value is 1250 and T5 is 800 minus T2 value is 550 and T1 is 300 plus T6 value is 600 and T1 value is 300. By solving this, we get 1250 minus 800 is equal to 450, and 550 minus 300 is equal to 250 divided by 1250 minus 800 is also 450 minus 550 minus 300 is equal to 250 plus 300. 450 minus 250 is equal to 200 divided by 450 minus 250 is equal to 200 plus 300 is equal to 500. This is equal to 2 by 5 in percentage into 100. This is 20. 2 into 20 is 40. That means 40%. Thermal efficiency will be 40%. Next question. A queuing system has one single server workstation that admit an infinite long queue. The rate of arrival job to the queuing system following the Poisson distribution with mean 5 job per hour. That means lambda is 5 arrival rate, and the service time of the server is exponentially distributed with mean 6 minutes. So 6 minutes means mu is equal to the service rate is equal to 60. We have to per hour, that means hour. 60 divided by 6 is equal to 10 jobs per hour. This is the lambda, and this is the mu. Mu is 10. So in steady state operation queue system, the probability that the server is not busy. So this is the ideal time. That means there is no not busy. That means no one in the system. So P naught is equal to 1 minus lambda by mu. Lambda is 5 and mu is 10. 1 minus 1 by 2 is equal to 0.5. So the probability will be not Bg equal to 0.5. The next question is a set of job UVWXYZ arrive at time t equal to 0. Production line consisting of two workstation 1 and workstation 2. The both workstation in a sequence, first followed by second, and the process in time minute is the job is given below. This is the time 5476 3648 6587, and then we have to find the sequences in which job must be processed in the production line if the total maximum time is to be minimized. So first workstation 1 and workstation 2, we have to make a table. That means jobs are six different jobs. We have to make a table of having 6 box 1 2 3 4 5 and 6, and the minimum time taken by workstation 1 will be taken as left, and the minimum time taken by the workstation 2 will be taken at right side. So first find out what is the minimum time taken by the job. This is the 3 and this is taken by W and produced by workstation 1. So this is the minimum and produced by workstation 1. So as I say, minimum time taken by workstation 1 taken as left side, so W will be left side. Next the minimum time is 4 and which is produced by workstation 1, so taken as left side, so this is X. Next minimum time is 4. This 4 is taken by workstation 2 and which is taken at right side, this is U. Next minimum time is 5 which is taken by workstation 2, it is taken at right side. Next minimum time is 6 which is taken by workstation 2, which is placed in right side. Next minimum time is Z, which is one box blank, so this is the WXZBYU will be the sequence WXZBYU. The first one is right answer. Next, the preparatory function in computer numerical control CNC machine programming are denoted by the alphabet. The preparatory function will be G code, so the option A will be correct answer. Next, the most suitable electromaterial used for joining low alloy steel in gas metal arc welding process will be low alloy steel, so the answer will be C. Next, the allowance provided to the pattern for easy withdrawal from the sand mold. The options are finishing allowance, shrinkage allowance, deterioration allowance, shake allowance. The answer will be shake allowance. Shake allowance is provided to the easy withdrawal from the sand mold the pattern. Next will be the grinding wheel used to provide the best surface finish. For best surface finish, we have to choose the grain size number as much possible from 80 to 80 onwards. So the answer will be A85 L5B, where the A is abrasion number, this is grain size number, this is hardness, this is series number, this is bond, this is vitrified bond. So grain size is 80, so this is the suitable for best surface finish. So option T is correct. Next, the earring phenomena in metal forming is associated. Earring phenomena is associated with deep drawing, where the die is punched between, and this phenomena is called earring. This is found in deep drawing material. Next, the phase present in perlite. Perlite present is ferrite and cementite. this is pure light. So that's all for today, and this is the all 1 mark question from GATE 2024. In the next class we discuss 2023 1 mark question. Thank you.